Okay, good morning. Hope you didn't get caught in the rain. So please scan this QR code and let's start with doing a few quick quiz questions. And can someone sitting at the far back kind of adjust the direction of the light a little bit? Yeah, it's glaring. Maybe like push it down or kind of make it face a bit toward that direction. It's not adjustable. Never mind then. Yeah. Oh, yeah, that'll be perfect. Yes, that's brilliant. Thank you. Okay, all good with the QR code? I'll give you 5 more seconds. 5, 4, 3, 2, 1. Okay. Time's up. Now, let's look at the first statement together. So here we have that the stationarity condition for an AR model of order 4 is that each of the 4 autoregressive coefficients is smaller than 1 in absolute value. So what it's saying that we require the alpha 1 to be smaller than 1 in absolute value, same for alpha 2, alpha 3, and alpha 4. Based on what we discussed on the higher order AR model, do you think this is correct or wrong? So this is a false statement, okay? Remember, that comes from slide 4, where we have that for the higher order AR models, okay? The key condition is that we require the sum of the coefficients to have an absolute value being smaller than 1. We do not require each of the individual coefficients to be smaller than 1 in absolute value, okay? The requirement is that all of them, okay, when we take the sum have an absolute value smaller than 1. So this is the condition behind the stationarity for higher order AR models, okay? We need to look at the joint behavior of all autoregressive coefficients together. A single coefficient is not sufficient to characterize the characteristics or the statistical properties of higher order AR models, because essentially a higher order AR models capture multiple lags, not just one lag at a specific, value of h. So this is a false statement, okay? Now, the next one. Increasing the number of lags included in an AR model improves the model fit, thereby reducing the residual sum of squares and estimation variance. So this is sort of built upon what we discussed on Monday, where we talk about when it comes to talking about model selection, selecting the optimal order for higher order AR models, okay? For those of you who just come in, I'll give you 5 seconds to scan this QR code. Okay, 5, 4, 3, 2, 1. Okay? Coming back to the second statement, do you think this is correct or false? So, I was about to say the majority wins, but then it suddenly becomes quite a balanced vote. So this is actually a false statement, okay? This statement sort of contemplates correct and misleading statements about the consequence of including more lags in the AR model. So first of all, okay, increasing the number of lags, that implies you increase more, past values of y on the right-hand side of the equation, which essentially means you included more regressors. more variables to explain the current observation. That does indeed improve the model fit in the sense of reducing the residual sum of square. It also increases the R square. Okay, that's always the case. Whenever you increase the number of variables included on the right-hand side of the on the right-hand side of the equation, you always have a smaller residual sum of square. Okay, well, maybe not always, but at least the residual sum of square never increases. Okay, it tends to decrease, and at the same time, the R square tends to increase. Okay, that's something we sort of discussed in topic 2 and also what we've seen on Monday. Now, a smaller residual sum of square and the estimation, so the residual sum of square and estimation variance, they're two different things. Okay? The residual sum of square sort of captures the variation in Y that has not been explained by the model, okay? Because the residual is the discrepancy between the fitted value implied by the regression function and the actual value of the underlying series. Whereas the estimation variance, that's basically the standard error of your alpha hats or the beta hats in the standard case. Okay, that's basically the inherent random variation in the estimated coefficients. There are two different things. And we've sort of already discussed that if we increase the number of variables included on the right-hand side, that implies there is an increasing number of parameters to be estimated. And given the same sample size, that would imply an increasing estimation variance. So this statement is correct if we omit the last part and estimation variance, okay? Increasing the number of lags thus improves the model fit and therefore reduce the residual sum of square, but it inflates the estimated variance, okay? So this is a false statement. And that's why we have the bias and variance trade-off, okay? Why we shouldn't indefinitely increase the number of parameters or increase the number of variables to be included in a model equation. Because there are pros and cons associated with increasing the variables on the right-hand side. On one hand, it might make your model better captures the underlying pattern of the series, but on the other hand, you're estimating more parameters, and therefore the estimated variance will increase, and that sort of reduces the reliability in your estimated coefficients because it just has a wider variance or a wider interval for it to sort of lie. Okay? Imagine if you plot the distribution of the estimated alphas, they will have a very wide distribution. Okay? So this is a false statement. Now, the next one sort of comes back to what we've seen in lecture 3, okay? So we have that the conditional expectation of a random variable given itself is always equal to itself. That should be quite a straightforward one, okay? So this is a correct statement, okay? Remember, we say that the conditional expectation of x given itself is equal to x itself. Okay, one way to think about it is that whatever that appears after the bar, okay, that is a given information. Whatever that's given, that is known. Okay? If you condition a random variable on itself, which is already known, of course, it becomes something that is settled. Okay? It's deterministic, so it must equal to itself. Another way to understand it is remember that the conditional expectation is essentially the solution to the best general prediction problem. Okay. Remember, we seek to find the optimal functional form of the given information, in this case x, that best predicts an outcome, okay, which appears on the left-hand side of the bar, and now it's the x itself, okay. Then what's the best functional form of x that best predicts x? It has to be itself, okay. So this is a correct statement. The conditional expectation of a random variable given itself is always equal to itself. And what it implies when it comes to what we've been doing so far is that conditioning on this big curly yt minus 1, okay, which captures all the information of y up to time t minus 1. So what's inside this curly big yt minus 1 is the immediate past, okay, the yt minus 2, yt minus 3, all the way back to y1, y0, and all the way back to the indefinite past, okay. All the history of y up to t minus 1 is given, and they're all embedded in this notation, the big curly yt minus 1. So that means, okay, whenever you have yt minus 1, the immediate past as the outcome that you want to predict, this conditional expectation must equal to itself because it's already given. Oops. Okay? And similarly, the conditional expectation of yt minus 2, given all past history of y, must also equal to itself, given that this is also given. And generally, the conditional expectation of any lag, okay, is just equal to itself for h that is greater than 0, because they are all included inside the big curly y, okay? So this is something that you should keep in mind in time series analysis, and this is something very important when it comes to forecasting, which we'll see later today. So this is the second last quiz question. Now the very last one, okay, we have that an AR1 model with IID white noise error, UT, and that is independent of all past observation of YT. So what we're saying is that if we have an AR1, which essentially takes this form, and we know that the error term is an IID white noise, okay, with mean 0 and variance sigma square u, and that we know that UT is independent of all paths of y, so it's independent to everything inside this big curly yt minus 1. This is what we know, okay? So given this structure, okay, or this model, this is mathematically equivalent to a simple linear regression model of yt on yt minus 1. So we're saying that this must be mathematically equivalent to the yt equal to beta naught plus beta 1 yt minus 1 plus, let's say, okay, vt, where we have derived this from what we've seen in topic 1, solving the best linear prediction problem. Okay, minimizing over the values of b naught and b1. And the solution gives us the beta naught and beta 1. So do you think that these two models are mathematically equivalent? Okay, the majority wins. This is correct, okay? And this is also the reason why it makes sense to estimate the AR model using OLS, okay? Remember, the OLS always consistently estimates the regression, okay? And given that they are numerically or mathematically the same, the OLS must also consistently estimate the AR model. And one thing you have to keep in mind is that the regression model, okay, this one is always obtained by solving the the best linear prediction problem, whereas this AR model is something akin to our causal model, although it doesn't capture causality. Okay? This AR model comes with assumptions. The error term follows IID white noise, and that it's independent of all past shock. These are assumptions. Okay? So, why they are mathematically the same? First of all, remember this beta naught and beta 1, they are the unique solutions to the best linear prediction problem. And we find the beta naught and beta 1 basically by solving the first order conditions. Remember, the two first order conditions in solving this minimization problem essentially give us two mechanical properties. One is that the conditional expectation, the unconditional expectation of the error term is always 0. And another one is that the error term is always orthogonal to the regressor. In this case, it's the yt minus 1. Okay? Remember in the cross-sectional case, we always have that expected value, let's say, of ui, that is 0, and that expected value of u and the x is 0, which sort of gives us that the covariance between the u and x, they are always uncorrelated. That's something mechanical. It's not an assumption. That's the consequence from solving the best linear prediction problem. And same here, we'll have that the covariance between b and yt minus 1 always being 0. Okay? These are mechanical properties. Now, this implies this together with the fact that we have unique solutions. So that basically means if our AR model satisfies the same set of conditions for the error term u, then alpha naught and alpha 1 must be the same as beta naught and beta 1. And clearly, we have that. Given it's assumed to be mean 0, we will have the expected value of ut being 0. And that the error term is independent of all past information of y, which is the strongest form of no relationship. That immediately tells us the covariance between ut and yt minus 1 is 0. Okay? So we have the same set of conditions satisfied for the error term, what we call the shock, okay? The surprise in the AR1 model, satisfying the same conditions as the error term coming from the population linear regression model. So the AR1 model, with the given assumptions, must be mathematically the same as the population linear regression model. Okay? So this is a true statement, and that's all the quiz question that I'll be looking at today. So coming back to model selection. So on Monday, we talked about the stepwise downward t-test, which is one way to identify the optimal lag order for an AR model. Now, today we're going to look at a different method for selecting the optimal P, which is called the information criteria. And the information criteria explicitly balance the bias and variance trade-off, okay? In a sense that they penalize the number of parameters included in the model equation, okay? We know increasing the number of parameters improves the fit. And one advantage of the information criteria, the IC method, over the stepwise downwards is that it's applicable over a lot of modeling contexts, okay? So the stepwise essentially can only be used to compare a larger with a smaller model. But the information criteria can be used to compare against models with the same number of parameters, okay, albeit they enter albeit the variables enter in different form. So remember in cross-section case, topic 2, when we talk about nonlinear specifications, we say that we can use a quadratic term, we can use polynomials, we can use logarithm. So imagine in a model where we have x entering either in a quadratic, another model x entering as a log. Okay? The two models have only one regressor. One is x squared, one is the log of x. There's no way we can decide which one is better by just simply looking at the R squared, the adjusted R squared, or doing some stepwise downward procedure. Okay? But the IC is useful in that case for determining which model is better in describing the Y. So this is one of the reasons why information criteria is very popular in econometrics literature for selecting models, not just for comparing against a smaller or a larger order of AR, but also in a lot of other contexts. So different from the R squared or the adjusted R squared case, the best or the optimal model here among the set that we're comparing against is the one that minimizes the information criteria. Okay? The one that comes with the smallest IC value is the one that wins against the set that we're comparing it with. And that means if the IC value is negative, you should pick the one that is the most negative. Okay? So that is how we decide on which model is the best. So in general, the information criteria, there are many different types of information criteria. Today we'll talk about the two most commonly used ones, which we'll see on the next slide. But all information criteria sort of takes the same form. The first term, okay, depends directly on the model fit, the residual sum of squares. Okay? So the M stands for the number of parameters included in the model. So it's the number of slope coefficient plus 1. Okay? The 1 stands for the intercept. So we have the first term that is for the model fit. And the second term, okay, that's a penalty term. This term increases with M, the number of parameters. Okay? So it's penalizing the increase of parameters included in a model to discourage overfitting. And T is the sample size, what is called, and here I sort of put it as the effective sample size. This is something very important in the case of time series. Okay? In cross-section, there's no such complication. In time series model, especially in models with autoregressive terms, that matters. So the effective sample size basically means the number of observations that could be fitted to the AR equation. Okay? So basically, this is something that sort of complicates the empirical analysis. And we'll see that in the practical session next week. So just kind of as a very straightforward or simple illustration. Okay. Imagine we have a sample, let's say, of 8 observations. Okay. So we have from 2021 Q1 to 2022 Q4. Okay, these are quarterly data. So there are 8 observations in the data set. But now imagine if we were to fit an AR1, then effectively, given that we don't have 2020 Q4, the first observation that could be fitted to an AR1 is the 2021 Q2, okay? The first observation to be fitted. Okay, this is the first Y that can appear on the left-hand side. Okay, whose immediate lag is the 2021 Q1. So essentially, the 2021 Q1 is the initial observation that should be set aside for an AI1, okay? This is the initial observation. Then effectively, given 8 observations in total in our data set, with 1 initial observation to be set aside, the effective sample size is 7, because only 7 observations starting from 2021 Q2 all the way to 2022 Q4 can be fitted to an AR1. Now, for an AR2, we need to include 2 lags on the right-hand side. Can we actually have the 2021 Q2 being fitted to an AR2 in this case? No, okay? Because imagine if we have 2021 Q2 here, that is the 2021 Q1, but the second lag is 2020 Q4. This is missing. Okay, it's not included in the data set. So effectively, we need to set an additional observation aside as initial observations. Okay, this doesn't work. The first one, it should start from the 2021 Q3. Okay, because then the immediate past is the 2021 Q2 and 2021 Q1. Okay, these are the 2 initial observations. And the 2021 Q3 is the first observation that can be fitted to AR2. Okay. So essentially, AR1 implies you need to set 1 initial observation aside. AR2, you need to set 2. For AR3, 3, AR4, 4, AR5, 5, ARP, P. Okay? So in this case, 8 total observations, 2 initial observations. That means we only have 6 effective observations to be fitted to an AR2. But when we are comparing across different models, okay, we need to ensure that everything is the same except for the number of parameters or the number of variables included. Then how can we ensure the same effective sample size for AR1 and AR2? Just set another initial observation aside. Just restrict the AR1 to be started from, okay, restrict the AR1 to start from the 2021 Q3. Then effectively, we will have 6 effective sample size to run the AR1, okay? We just omit the 2021 Q1, that's useless, okay? We don't need to consider it when comparing different models. This first observation that we start running the AR1 is for 2021 Q3, which uses the 2021 Q2 as the initial observation. Okay? So this might seem a bit confusing at start, but next week during your practical session, you get to see what it really means when you have a data set to analyze at hand. The next practical session will be built upon the NILE data set that we've seen in practical session 1. You'll be doing model selection and you'll be doing forecasting. Okay? So just remember, in theory, we need to make sure that the T, okay, the effective sample size, to be the same across all models that we're comparing. If we're comparing AR1 and AR2 in this specific case, then we need to ensure that the effective sample size is just T equal to 6 for both models. Yes? What do you mean? It's F is a function of T and M. and we'll see what function it is. Okay? The specific functional form of the penalty term depends on which information criterion you're looking at. Okay? The first term is always the same for all types of information criteria. The information criteria only differ in terms of the second term, the F. Some of the IC has stricter penalty. Some of the ICs has a less stringent penalty. Okay? So that brings us to the, I really don't know how to pronounce this properly. That's Japanese. I think it's Akaike Information Criterion, or you just call it AIC. Okay? Everyone calls it AIC in the literature. But you really need to know that the A stands for a name of an econometrician and statistician. The A doesn't stand for average. Okay? The A stands for Akaike. So it's the AIC. And we can see that the AIC has a penalty term, which is equal to M, the number of parameters, multiplied by 2 over the effective sample size, T. And another commonly used IC is the information criterion. So the penalty term also depends linearly on M, the number of parameters, and also the effective sample size appears in the denominator of a fraction. But what is different is that in the numerator, instead of having a 2, we have the natural log of T. So the natural log of the effective sample size is essentially increasing in the sample size, whereas 2 is always fixed. Okay? So the BIC always gives a larger penalty than the AIC, especially as T, the effective sample size, being greater than 7. This is immediate when you plot the logarithm function. Okay? The logarithm function, loosely speaking, okay, it looks like this. And once, let's say this is T here, this is log of T. Okay, once it passes 7, it will be greater than 2. So the penalty term is always larger for the BIC, because typically an empirical data set will definitely have more than 7 observations. Okay, and usually we will have at least 30 observations, or in most cases more than that. So the BIC has a larger penalty compared to AIC. Okay? And remember, for an ARP model, M is equal to P plus 1. P is the number of lags, the number of slope coefficients, and 1 is the intercept. And another thing that you should take away is the information criteria is a relative measure. You should only use it to compare against different models. Okay? The information criteria of one given model doesn't tell you much. Okay? It's not an absolute measure of how well the model fits the data. Okay? It's just like R-squared or adjusted R-squared. Looking at them alone doesn't really make any sense. So while both AIC and BIC, they lead to reasonable model choices, AIC tends to choose a larger model because it has a less, the penalty term is smaller, okay? So it's less conservative. And BIC tends to choose a smaller model because it has a heavier penalty, okay? The heavier the penalty, that was sort of implies if you attempt to increase the number of parameters, okay, the BIC would tend to increase by more than the AIC, okay? So AIC tends to choose a larger model, BIC tends to choose a smaller model. Now, it's very typical that different model selection methods might end up choosing different optimal order. And that's something that's natural because the decision depends on how the criteria or the method of selecting the optimal order is designed, okay? Now, if AIC and BIC and maybe the stepwise procedure choose a different optimal order, okay, that doesn't mean that there isn't a sort of like a unified agreement. How we should proceed from there would depend on what you're interested in. For example, we're interested in forecasting, okay? If AIC, BIC, stepwise downward, they all choose 3 different orders, then we should proceed to forecasting using 3 different model specifications. And then we compare their forecasting performance. Okay. By comparing their forecasting performance, we might end up being able to select one that is the best for doing forecasts. Okay? So that's how we typically proceed if we end up having different optimal orders selected according to different methods. So this is just an example using the growth data that we're familiar with. And I've sort of restricted the effective sample size across all AR models. Okay, so here we have the results for AR1 to AR6. And we can see that the effective sample size is all 198 across all different AR models. Okay, that ensures fair comparison. Now, the M is essentially the number of parameters to be estimated. Okay, P is the order of lags. So we can see that P is 1, M must be 2. When P is 2, M is 3. So M is always one unit greater than a P. And we can also sort of see that, okay, as P increases, which effectively means as the number of parameters increases, the residual sum of square, okay, the row corresponding to the RSS is always decreasing. Okay? That means without the penalty term, we'll always go for the largest model because it has the smallest RSS. Okay? And we can also see that for the R square is increasing in the number of parameters. Okay, and that will also mean if we don't penalize the number of parameters and we use R square alone as a model selection method, R square will always choose the largest model. Okay, and this is the reason why we should never rely on RSS or R square alone to choose a model, because they always favor the largest one, which would risk overfitting and also inflated estimation variance. Now, we can see that the adjusted R square, remember the adjusted R square adjusts the R square for the number of parameters included. It's penalized the number of parameters. And we can see here the adjusted R square is not uniformly increasing in the number of parameters. Okay? When P is 1, it's 0.11. It increases, increases to 0.135 when we have an AR2. But then it decreases again, okay, for 3 and 4, and then for AR5, it goes up. So the adjusted R square, okay, it basically balances the bias and variance trade-off. But it has the tendency to choose a larger model because its penalty is the lightest among AIC, BIC, and itself, okay. You can see here, if we use adjusted R square as the criteria to choose the optimal order, it will go for an AR5 because the adjusted R square is the largest, which is 0.139 among all 6 models that we are comparing. Okay? So these are the 3 metrics that we've already seen in topic 2. Now, what's new today is the BIC and the AIC. And before looking at their value, okay, the BIC penalty and AIC penalty explicitly gives the value of the penalty term. Okay? So the BIC penalty is the value of the m times the log of t over t for each model. So we can see that the penalty term is increasing with the number of parameters. And the AIC penalty, which is equal to m times the 2 over t, it's also increasing in the number of parameters. And if we compare the two penalty terms, we can see that the BIC is always larger than the AIC. Okay, so the BIC imposes a heavier penalty than the AIC, resulting it tends to choose a smaller model. Okay, its resistance against increasing the number of parameters. Now, if we look at the second last row, that gives you the value of the BIC for each model. And remember, the one that we want to choose is the one that has the smallest BIC value. So here, it's the 2.35a, okay? Because the last three, the value is like roughly 2.4, which must be higher than the first three. And out of the first three order, it's the AR2 that minimizes the BIC. So the BIC would tend to choose an AR2 as the optimal among the 6 models. And similarly for the last one, AIC, we want to choose the smallest as well. And we can see that here, AIC and BIC gives the same choice, okay? They both choose an AR2 as the optimal order. And this is the same as the result that we've seen when we've done the stepwise downward procedure on Monday, okay? The stepwise downward t-test also favored an order of 2. So, So in this case, okay, we've seen that the AIC and BIC agrees as the same number of order. In a practical session, you'll see that AIC and BIC doesn't agree on the optimal order, just as a comparison, okay? So before I finish today, so some of you might wonder, should we allow gaps in the AR models? So for example, instead of including the first up to the 4th lag, should we just include the first and the 4th and omitting the 2nd and 3rd? Okay? And there's a yes and no. You shouldn't do this without prior information or without theoretical justification, okay? You should only do this with a good reason in believing you should only keep the first and the 4th lag in a given context. Or let's say if you have a monthly data, then you might want to keep just the first 6 and the 12th lag, accounting for the annual effect, okay? But if you don't know which lag to keep, then it's always good to keep all of them without allowing for gaps, okay? Because if you don't know which specific one to choose, then you would end up having to let the model selection method to choose them. But think about it, okay? Imagine if we have 4 possible orders, okay, from AR1 to AR4, and then you only want to keep 2 of them. So it's 2 to the power 4 of possible choices that you can choose. So that is computational heavy. You don't want to do that. So only allow for gaps if there is a good reason behind it. So that's it for model selection. I don't have the time to talk about forecasting today, so I'll do it on Monday, okay? But we'll be on a good track in finishing time series by week 6, I think. Now, final thing before I let you go. So just before I wrap up, okay, I sense a lot of you might be interested in knowing this. So I just want to give you a brief overview of the collective or the average performance in the semester 1 final exam. You get to know your own final marks from the assessment team maybe later this month or early in March. Don't worry, you have this on Blackboard. I'll upload it later today, okay? So on average, and okay, one thing before I comment, these summary statistics, okay, they are just raw ones. They are subject to internal moderation, which typically happens at the end of the academic year. So we can see that on average, you did a good job. I'm really happy to see at least half of you got a 60, okay, because the medium is 61.5. That must mean at least half of the class scored a 2-1. And we also actually have roughly 30% getting a first, okay? Even though a lot of you were complaining that econometrics was hard, but you rock it, okay? So well done, and I think this is a testament to all the hard work that you put into for this course. Remember, active engaging with all the course material is the key. Now, what happens in semester 1? That's in the past. Okay. What's more important is semester 2. Whatever the outcome is in the first semester, okay, whether you have surpassed your expectation, you meet your expectation, failed to meet your expectation, that's in the history. Semester 2 counts 50% as well, and in the end of the day, it's the weighted average of both semesters that matters for your final mark. So those of you who've done a good job, keep up the good work. Those of you who face challenges, maybe think of it as a chance to reflect and adjust, okay? There's always room for improvement, and my office is always there, okay? My door is open whenever you want to ask some questions, or you just want to seek for advice, or you just want to chat. Feel free to come. Now, I would encourage you to go through the questions, okay, which is after the summary statistics. Basically, it links every single question back to either some material on the lecture slides, some material in the practical session or the tutorial, or in your homework, okay? So in order to excel in this course, you really need to make sure you attend the lectures, go through all the materials, go to the practical session and the tutorials, and do all the worksheet and homework. Okay, so thank you and have a lovely weekend. I'll see you on Monday.